We should go into chapter 12 after we finish up the last little part here of 11. So the last time we were talking about chemistry, I think. So we're talking about alkenes, alkynes, addition reactions that they undergo. So remember that pretty much an addition reaction is when we add two things in. And where we do that with alkenes is through that double bond. And to make room for it to add, we do have to make that double bond into a single bond. And by making it into a single bond, that allows both of those guys to be added. So whatever's coming in, say it's Br2 or HOH or HBr or whatever it may be, we take that double bond, we make it a single bond, and then one goes to one carbon and one thing goes to the other carbon. The only time you really have to sort of worry about where things are added is a situation where in the double bond, one of the carbons have more hydrogens. So if a carbon in that double bond has more hydrogens and you're adding something with hydrogen like HOH, like for water, or HCl, HBr, the hydrogen coming in will go to the carbon that had the most hydrogens to begin with. The other guy will go to the other place. We also talked about cis and trans isomers that basically develop from those double bonds. And in order to have a cis or a trans isomer, you basically need that double bond. And on each of the carbons, they do need to have two different groups attached directly to them. And they also need to actually share a group in common on both sides of the double bond. And if those groups that are shared on both sides of the double bond are on the same side of the double bond, that's what is referred to as the cis isomer. And if those groups are sort of opposite of each other on the double bond, maybe one up, one down, that is what is referred to as the trans isomer. Any questions on any of that stuff there? I think that we talked about last time. All right. So to sort of finish up here, we're going to talk about aromatic compounds. Aromatic compounds do contain the benzene ring. So I think we've seen it a couple of times, but this is basically your benzene ring here. It's really a 6-carbon structure, as we can see over here. And there's basically 1, 2, and 3 double bonds in the benzene structure. Can be drawn like that. You could also draw a resonance structure of that, where basically our double bonds are on the other side. And very often, especially like in our books and stuff like that, they sometimes will just kind of lay up a circle there in the middle to indicate that those double bond electrons really can move around and can be in any location. So those are sort of 3 different versions of the benzene ring. Again, not to be confused with cyclohexane that we've seen earlier. Cyclohexane is this guy. Again, there are no double bonds in that guy. So again, that's a cycloalkane, while obviously this is a sort of class of compounds which are aromatic. Because they do have these double bonds, what we essentially get happening here is 3 electron pairs and 3 bonds. So it takes on that trigonal planar geometry, that 120 degrees in terms of the bond angle, and it sort of lays it very flat on a plane. And again, if you're wondering where that sort of 3rd bond is, again, each of these have a hydrogen. So basically 1 bond, 2 bonds, 3 bonds, and also 3 electron pairs there, which is our trigonal planar geometry. Each of these guys, again, our double bonds are in some different arrangements. The physical properties of aromatic hydrocarbons are similar to regular hydrocarbons. Again, there's pretty much all carbons and hydrogens, so they're typically insoluble in water like we would expect normal hydrocarbons. They also have low melting points and boiling points, again, because they're going to be essentially using that dispersion forces as their intermolecular forces, so they're not going to have very kind of high boiling points or melting points, as dispersion forces are your weakest sort of arrangement of intermolecular forces. Here's some drugs. Again, you see our benzene rings in this particular guy. It actually has 3 different benzene rings, which makes it sort of aromatic. Now, when we do have one sort of group that is substituted on the benzene ring, when we name it, we essentially just pretty much name the group and kind of put benzene at the end of it. So here's our benzene ring, and attached to our benzene ring is a 2-carbon group. Again, the 2-carbon group being ethyl, and we get to the name of ethyl benzene. Again, here, no need for a number or anything like that because there's only one group attached. Wherever that group's attached, it's assumed to be carbon number 1. And same thing over here. Here's our benzene ring. Again, we have a 4-carbon group attached to it. So that's a butyl group. And again, butyl benzene. And lastly, we have a chloral group here giving us chloral benzene. So not too bad in terms of the naming part of it. You essentially just put benzene at the end, and you do put whatever the group is in front. Now, benzene is interesting when you do have some benzene guys here with certain groups attached. There are some sort of historical names that are very commonly used and still sort of used. So there are some arrangements here, and we should be aware of some of these because they do still pop up a lot, especially these 3 here. So if you have a benzene ring with a methyl group at the end, it technically is methyl benzene, but it has really a historical name known as toluene, and people really still use that name a lot. So if you see somebody say toluene, it basically refers to a benzene ring with a methyl group on it. And again, this name does pop up a lot. Again, it's one of those sort of historical names that is still used a lot. This is really an alcohol here. We have an OH group on our benzene ring. And again, this would be hydroxybenzene, hydroxo because that's the hydroxy group. And it also is known more so by this name. And this is a name that is still very commonly used most of the time. So phenol there, again, is a benzene ring with an OH group. Again, not to be confused with what we maybe have talked about as well. Something like this. This is cyclohexanol. Again, that is not a benzene ring. So again, that's why it has a different name. No double bonds in that guy. And lastly here, this is also one that is used also still very, very common. And this is what is known as aniline. It's basically a benzene group with a NH2 on it. And sometimes the NH2 is known as an amino group. So that's where that name comes from. And that is aminobenzene. But I would say for us, you should be familiar with these 3 names here and what it represents because it is still used a lot still along here. Yeah. So most of, if I understand your question, most of what we're talking about, a lot of it is memorization. You do need to be able to obviously give the names of things. You'll need to be able to draw a lot of those structures that we had to draw as sort of results of reactions, and obviously draw formulas of things with names. So it is definitely some memorization, but you still need to. There's really no calculations, but you still need to be able to obviously draw a lot of these things, some of which we've done before. Now, when we do have multiple groups that are on a benzene ring, we do want to number it, and we want to number it in a way that gives, again, the group the smaller name in terms of alphabetical order. If there's no difference, then it really doesn't make a difference. So for example, on all 3 of these things, we basically have an ethyl group on each of these. And in this case, because they're both ethyl groups, you can number 1 and 2, which would be the proper way of numbering that. And that's what gives us our 1,2-diethyl benzene. Now, when you have a benzene ring and you have a group that is located at carbon 1 and carbon 2, that is also what is known as the ortho positioning. So instead of using numbers, it is still very common that people will use ortho diethyl benzene, or just O to indicate ortho positioning. So if you see the ortho positioning, R and O in front of a name, that represents the 1 and 2 positioning of those groups around a benzene ring. Here we would have 1, 2, and 3, giving us 1,3-diethylbenzene. Now, the 1,3 positioning along the benzene ring is what is known as the meta positioning, and also abbreviated sometimes with just M. So if you see M or you see us say meta, that means, again, you have a group located on the benzene ring at positions 1 and 3. And lastly here, this would be 1, 2, 3, and 4. So 1,4-diethylbenzene, and the 1 and 4 positioning along the benzene ring is what is known as the para positioning, or sometimes abbreviated with just a P. So again, sometimes these ways of naming it, ortho, meta, para, is oftentimes used. Again, it is used in place of the numbers, or if you see it, it means a certain set of numbers. So you do need to know ortho, meta, para, what it means. 1, 2 for ortho positioning, 1, 3 for meta, and 1, 4 positioning for our para. Any questions on that there? And as I said, if you have multiple groups here, we do want to sort of put our groups in alphabetical order. So here's our benzene ring. We have a bromine and a chlorine here. So B before C. So if you were to number this, you would give it the 1 and 2 location in terms of its numbering. Again, the 1 and 2 location is the ortho. So that is ortho, bromol, chloral, benzene, are 1 bromol, 2 chloral, benzene. Again, without using the, I just finished spelling that, without using the ortho here, or the without using that ortho, you could put the numbers in. Here we have basically fluoral and ethyl. Again, ethyl would come first. So if we were to number this, we would want to give the ethyl the smaller number. So 1, 2, and 3. And that technically would be 1 ethyl, 3 fluoral, as I run out of room there, and benzene, if you wrote the whole name out, are again eliminating the numbers. You could go with meta, ethyl, fluoral, benzene. Again, the meta symbol there, or the M symbol, indicates the positioning of those guys at positions 1 and 3. Any questions on that there? Now, as I mentioned before, sometimes there are historical names. So here we have our benzene ring that has that CH3 group, and that is the toluene part. And from that, this is 1, 2, 3, and 4. Basically, our bromine is a 1-4 relationship. So that is why the para is here, para bromol toluene. Again, if you did not use sort of that historical name, you would do probably something like 1 bromol, 4 methyl benzene would be sort of the non-historical name use of it. Also here, if we look at what's in the box, we have our benzene ring with the OH group. That is our phenol. And again, it is basically 1, 2 positioning between those two. So that's going to be our ortho here. And that gives us orthochloral phenol again, using that as a 1, 2 positioning. Our 1, 2 coming this way, which is probably the right way since that guy technically would come alphabetical first. Any questions on that there? Yeah. So as I mentioned before, when we have multiple guys there, we do want to number whichever way gives the group the smaller number. And in this case, because it is in a ring structure, we want to go alphabetical. So whichever group sort of gives, whichever way gives that alphabetical group, the lower number is how you would want to number it. And that guy would normally be number 1, wherever that may be. So here, if we look at this, here we do have, again, the main thing is our benzene ring. We have an ethyl group we have a propyl group, we have a chloral group in this particular case. And what we would have is 1-ethyl 2-propyl benzene here with our 4-chloral in this particular case. Based on sort of where things are located, I think, if we went this way, 1, 2, 3, 4, 5. So again, going this way would give us some larger numbers there, 1, 4, and 5 versus 1, 2, and 4. So that's why they kind of went that way in terms of the numbering. So they didn't really go alphabetical here. They went whichever way gave our multiple groups sort of the smaller number. So at carbon 4, we have a chloral, 1-ethyl, and 2-propyl benzene in that particular case. Now, when we do have this, again, if you can kind of see that historical name in there, you can use that aniline as the root and then sort of give the location where we find the rest of the guys. We have our dichloral there, so 2,5-dichloral aniline, this guy being carbon number 1 and coming around 2 and 3, again coming this way, gives us a 1 and 2 versus a 1, 2, and 3. Again, bigger numbers kind of going this way. So we would want to go counterclockwise in this particular case. So let's see how we get to these names here, just to make sure. So looking at this here, we have an ethyl group right here. We have a bromol group right here. And again, we could go 1 and 2, and that gives us our 1-bromol, 2-ethyl benzene. Again, this is our 1 and 2 positioning, which is our ortho-bromol ethyl benzene. Going to the bottom one, we have a chlorine group here, a chloral group here. That is 2 chloral groups, gives us dichloral benzene. Again, numbering whichever way you want to kind of go gets you the same result. You have a 1,4-dichloral benzene, 1,4 positioning, again going to be our para positioning. And lastly over here, kind of stuck right about there, that is our benzene group with the methyl group at the end, and that is where the toluene comes from. NO2, one way to naming that is a nitro group, and it would be at carbon 1, 2, and 3, and that 1, 3 positioning would be our meta positioning there. Any questions on any of those names there? All right, so take a second here and decide which is the correct name on each of these. Okay, let's take a look and see here. So again, we have our benzene ring, obviously, and we have one group attached, which is a chloral. And again, because it's only one group attached, chloral benzene will work there. Again, it's not cyclohexane because that has no double bonds, and you don't really need the number here because it's only one group attached. For our second one, we do have our benzene ring as well, and we have 2 methyl groups. So we have some dimethyl benzene happening. Position-wise, this is 1, 2, and 3. So it is 1,3-dimethylbenzene. 1,3-dimethylbenzene is also the meta positioning, and again, could also be named something like this. Any questions on those two? Okay, so why don't you draw these? So draw these two guys, see what you come up with. Okay, so just like anything else, we're going to start backwards. So backwards on these guys are pretty simple. It's benzene. So you do want to draw your benzene ring. Again, you could put the double bonds in. You could do the circle in the middle if you like, whichever way you want to do it. Dichloral means we have two chlorine groups, and they are carbons 1 and 3. So if I just put my chlorine up here, that would be carbon 1. This would be carbon 2, and that means carbon 3 would be right about there. And that would be our 1,3-dichlorobenzene, also our meta-dichlorobenzene. Again, the 1,3 positioning happening. Starting on the back end here, we have toluene, which isn't just straight benzene. So remember, toluene is one of those kind of historical names for benzene, and that is basically a benzene with a methyl group. So that is the toluene part. Since this is kind of the main part, this would be carbon 1, which means that carbon 2 is where we have our other group located, which would be right about there. And that is the 1,2 positioning, are also the ortho positioning. Orthochloral toluene could be another name for that one. Question on those two there. All right, so to kind of finish up this chapter, we're going to talk a little bit about a reaction that basically benzene rings undergo. And benzene rings pretty much undergo a substitution reaction. So they undergo a substitution reaction just like alkanes. And just like alkanes, what's going to happen is pretty much one of these hydrogens is going to come off. And Cl2 is basically two Cls, and one of those is going to come on in its place. And again, if we look over here on the right-hand side, absolutely everything here is exactly the same. Absolutely nothing else has changed. So those are both identical to each other. The only difference is basically we popped off a hydrogen and we put the chlorine on. And that means that the hydrogen that came off will hook up with the other chlorine there and make HCl. So that's where that sort of comes from. By the way, this is just sort of a catalyst. It's not really involved in anything. The iron doesn't go anywhere or anything like that. It's just there to kind of make the reaction happen kind of quicker. So usually when you see something kind of written on top of the arrow, 9 times out of 10 is probably not going to sort of do much in a reaction. So we technically could have pulled off any of these hydrogens. They're all equivalent hydrogen, which basically means they're all the same. So you technically could have pulled off any of them and replaced it. Kind of like the alkanes, we probably would do just a mono substituted, which just means we're just going to take one of the hydrogens off and put one of the chlorines on. Any questions on that reaction there? All right, that should wrap up chapter 11, I think. Yeah, so if you had toluene, it probably would not necessarily go to the methyl group. It probably would hit one of those unsubstituted ones around the ring, if that's your question. So, for example, if say we kind of put a CH3 there, it probably would hit one of these other hydrogens in terms of the substitution. It would most likely would occur. Again, it's a lot easier for it to pop off one of these guys around the ring. When it tries to come into here, you know, it's got a couple of carbons. It's got to kind of intrude with in those hydrogens. So usually more so it would probably be a hydrogen on the ring in that case. Other questions? Okay. Then we're off to chapter 12 now. And chapter 12, we're going to talk about basically the carbon-oxygen double bond, alcohols, ethers, thiols, aldehydes, and ketones. So all that good carbon-oxygen double bonds happening. So in this sort of chapter, we'll talk about alcohols. So as we talked about earlier, alcohols have that OH group as the functional group. It is a polar group where the oxygen is more negative, hydrogen is more positive. We will also see ethers, and the functional group of an ether basically is a carbon, oxygen, carbon type of run. And that's the functional group there. And we'll talk about some of the properties of that. As we can see, alcohols end in OL. Ethers, common way of naming it is group to the left, group to the right of the oxygen. They're both ethyl groups, diethyl ether. And we'll get into naming a little bit more in a second. Whoops. We'll also see some alkyl halides, although we sort of covered that a little bit with alkanes. This is basically two carbons with a chlorine group on it, and this is chloral ethane. We will also see these are alkyl halides. Halides means halogens. So it's basically a carbon group that contains halogens attached to it. We will see thiols. Thiols are sulfur-containing groups. So the SH is our functional group here. Kind of very similar to alcohols and sort of its properties. So we'll see some of those in this chapter as well. Aldehydes and ketones are the other two kind of big groups that we will see along here. Aldehydes have the functional group of carbon oxygen double bond and a hydrogen, and ketones have the functional group of basically three carbons in a row, and in that center carbon you have that carbon oxygen double bond. Remember that the carbon oxygen double bond has a special name. That is what is known as the carbonyl group. And this is sometimes referred to as the carbonyl carbon. It's really a polar group, as we'll see, where the oxygen is more negative, the carbon is more positive in that bond based on electronegativity, just like we talked about sort of with bonding. So the first one we're going to talk about is alcohols, and I know we kind of talked about it, so hopefully this will be a good review of what we talked about there in discussion last week or so. Alcohols, again, have that functional group of the OH. Again, it is a polar group, negative and positive. That negative and positive, it does allow it to do some hydrogen bonding because of that. And as we talked about in discussion as well, we can classify our alcohols as primary, secondary, or tertiary. And the important thing to look at is the carbon that has the OH group attached to it. And attached to that carbon is one more carbon directly attached to it, and that is what refers to a primary alcohol. So the carbon that has the OH group attached to it has one more carbon attached to it, and that makes it a primary alcohol. A secondary alcohol, much like a secondary carbon, again, our carbon that is directly attached to the OH group is connected to directly one and two other carbons, making it a secondary alcohol. And lastly, our tertiary alcohol, our carbon that is attached to the OH group is attached to one, two, and three carbons directly to it, which makes it a tertiary alcohol. So that's an important sort of distinction in terms of alcohols, in terms of sort of classifying them, as we kind of talked about as well. Different alcohols will do different types of reactions. So alcohols, because they do contain that OH group, pretty much has 4 electron pairs, and for 2 bonds, and it has that bent or V shape to it. That's that 109.5 shape degrees that we talked about with bonding. And again, because it does have that OH group, it makes it usually very soluble in water, especially small ones. And they're soluble in water because when water comes around, it pretty much has the identical bond happening there. And between our alcohol and water, they're able to hydrogen bond. And if you remember from our talk of intermolecular forces, hydrogen bonding is a very strong intermolecular force. So what that means is because alcohols have that ability to hydrogen bond, we do see very high boiling points and melting points for alcohols. So we see higher boiling points for sure because it has that ability to hydrogen bond. When they hydrogen bond to each other, they create a very tight bond, and it takes a lot of energy to break that. A lot of energy to break that is what you need to do when something goes from liquid to gas at its boiling point. So more energy to do that requires a higher boiling point. So in terms of winning the race, in terms of boiling points between an alkane like we have here and an alcohol like we have here, the alcohol is definitely going to be the winner because of that ability to hydrogen bond. So as we go through these different organic groups, oftentimes we talk about things like, which one would we expect to have the higher boiling point, and really anything that has that ability to hydrogen bond is always going to have that higher boiling point because of that really strong intermolecular force. So you can just see the comparison there. The butane is minus 0.5 degrees Celsius in terms of its boiling point, while the alcohol there, because of that OH group, has a boiling point about 97 degrees Celsius. So a very significant difference in the boiling points here. Because of that stronger intermolecular force, we see higher boiling points and higher melting point. So sort of our winner in terms of different organic compounds that we've talked about so far is the alcohol. The alcohol is still going to be here the highest in terms of boiling points. Alcohols, like I said, usually about 6 carbons or less, are usually fairly soluble in water. And again, it's because they have that OH group, it allows them to interact with water really well. When you do sort of go more than 6 carbons, and what happens is as you build out more carbons, just draw an insane amount of carbons here, and maybe you just have that one OH group at the end, all these carbons would have hydrogen. So you got this giant part of the molecule here that's going to be nonpolar. You got this one little part over here that is polar. And what ends up happening is when you build out more than 6 carbons in an alcohol is we get what is sometimes referred to as steric hindrance, which basically means this big old part here gets in the way of this alcohol being able to really interact with water really well. So that's why kind of small alcohols, 6 or less carbons, they're not so big, that nonpolar part, that it sort of gets in the way with the interaction of the alcohol with something like water. So something like what we see here, ethanol on the left is pretty water soluble. We get up to about 8 carbons. It's pretty much insoluble in water. Also, if you have multiple OH groups, so if you happen to have an alcohol with multiple OH groups, which can happen, the more OH groups that you have on a compound, the more soluble it would be in water, because everywhere you have that OH group gives water pretty much a place to interact. Any questions on that there? Okay. So let's talk about naming. So when we name alcohols, we essentially drop the last part of the alkane name, and we do put the OL. When we do name an alcohol, it is the OH group that takes the priority in terms of the numbering. So we really follow the same sort of rules as we've seen before. For example, the simplest sort of alcohol you could have is a 1 carbon alcohol. And one carbon is based off of methane, and we drop the last part of methane and it becomes methanol. No need to give the location of this because there's really only one carbon, so it's got to be carbon number 1. Same thing if we had, say, 2 carbons over here. Two carbons is based off of ethane. It has the OH group, so it becomes ethanol. Also, really no need to give a number here because this would be carbon 1, although if I put the OH group over here, this would then be carbon 1. So it's really the same carbon. It's just turned around. So usually once you hit right around 3 carbons, you do need to sort of give the location of where that OH group is located. So if you had 3 carbons, where we have the OH group there in the center, 3 carbons would be based off of propane, and it becomes propanol, and our OH group would be at carbon number 2. So 2-propanol would indicate that the OH group is at carbon number 2, and we need that when we hit 3 carbons because we could have that OH group at carbon number 1 in this particular case. And this would be known as 1-propanol. So 1-propanol is different than 2-propanol, and about 3 or more carbons, you do need to give the location, again, of where you would find that OH group located. Some things do have some other names. 2-propanol is also known as isopropyl alcohol because that is the isopropyl group. So this is isopropyl alcohol. Kind of a common name. And we also know that as rubbing alcohol as well. So that's also the name of it. But the official kind of IUPAC name would be this kind of 2-propanol sort of name. Any questions on that there? So again, we want to look for the longest carbon chain. When it is an alcohol, that longest carbon chain does need to contain the OH group. So if we look at something like this, 1, 2, 3, 4, 5 straight across, 1, 2, 3, 4. If you go up and over, if you go from the down and up, 1, 2, 3, 4. So 5 carbons straight across, going to give us our longest carbon chain of 5. That's based off of pentane. Here it's an alcohol because it has an OH group, and that would then make it pentanol. We want to give the OH group the smallest number, which means we would want a number 1 over here. That means that is 2, that is 3, that is 4, and that is 5. And that means I believe we have a methyl group at carbon 3 and another methyl group there at carbon number 3. And that would be something like 3,3 dimethyl for the 2 methyl groups, pentanol in this case. So we do want to kind of go the same sort of method, longest continuous carbon chain. Here it does need to contain the OH group because it's an alcohol. The OH should always get the smallest numbering based on whichever way you need to do that. And once you pick the way you numbered based on the OH group, all the other groups should be numbered accordingly because of that. And that's hopefully where they should end up there. There we go. Now, if we do have sort of a ring structure here, we kind of will do it a very similar way. Again, the big part here with the OH group is going to be our alcohol. So that is a 6-member ring, which is cyclohexane. Because it has the OH group, it becomes an alcohol. So we drop the last part of that. And that's where we get our cyclohexanol. That leaves one group left over here, which is a methyl group. And since this is part of the functional group, it should have the smallest number. And we could either number 1, 2, 3, 4, 5, or we can number counterclockwise 1, 2, and 3. So we would want to go this way, as that would give the group the smaller number. And that's where we get our 3-methyl cyclohexanol. Question on that name there. All right, so we got a few here. Why don't you give those guys a second here and give the name of those guys, see what you come up with. And while you're at it, why don't you also see, are these primary, secondary, or tertiary alcohols? See what you come up with here. Okay, so let's take a look, see how we're doing. So looking at the first one, there's actually multiple ways. We go straight across. You got 1, 2, 3, 4 carbons. You could also start at the top and come down to the right. 1, 2, 3, 4 carbons. So it does look like 4 carbons is our winner here. Might as well just take the straightest move there. So 4 carbons, it's going to be based off of butane. It's an alcohol because it has the OH group attached. So that is going to be butanol. Remember that we do need to give the location here of the OH group, and we want a number, whichever way is going to give it the smaller number. So that in this case is going to be right to left here, 1, 2, 3, and 4. That gives our OH group carbon number 2 as opposed to carbon number 3 if we went the other way. So that would give us 2-butanol. That CH3 group would be the last group that's left. Because we locked in terms of which way we're numbering, that means that our CH3 group is going to be at carbon number 3, and this would be 3-methyl 2-butanol. First off, any questions on the name? Okay, we want to know, is it primary, secondary, or tertiary? So to determine that, we want to go to the carbon that is attached to the OH group. And attached to that carbon is one carbon there and two carbons there. So this would be a secondary alcohol because of that. Coming to our right here, we have really a cyclohexane ring that has an OH group on it. So that is based off of cyclohexane. Because it does have that OH group, that's going to be cyclohexanol, OL at the end of it. And in this particular case, this is going to be carbon 1. This would be carbon 2. This would be carbon 3. So this would be 3-methyl cyclohexanol. Again, you don't really need the number here for the OH group on this because it is a ring. So wherever that is located, it's always going to be assumed to be carbon number 1. So that's why we would not probably put the number there in front of the cyclohexanol. Coming down to our guy on the left here, looks like we have 3 carbons. You could go a couple different ways to do that, but might as well just go straight across. So 3 carbons is based off of propane, becomes propanol. Location of that OH group, no matter which way you go, is going to be carbon number 2. So that is 2-propanol, leaving our methyl group also at carbon number 2. And that would be 2-methyl 2-propanol. Any questions on that particular one? And lastly here, we have 3 carbons in a row with nothing else attached. And we do give the location there as 1 and 2. And this would be 2-propanol. In terms of classification, I think I missed that part here. So looking at the guy on top right, this is our carbon that's attached to the OH group. It is attached to 1 carbon there and also another carbon there. And that would make this one also a secondary alcohol. Over here, this is the carbon that is attached to the OH group. And that is attached directly to 1, 2, and 3 carbons. So this would actually be a tertiary alcohol. And lastly here, this is the carbon attached to the OH group, attached to 1 carbon and 2 carbons. This would be your secondary alcohol. Any questions on any of those names or the classifications? All right, so just looking at this one here, let's just talk about sort of name and classification. So again, we have 1, 2, 3, 4 carbons with the OH group at the second one. So this is going to be our 2-butanol. Also going to be a secondary alcohol. Again, that carbon's attached to 2 other carbons. This is going to be 2 carbons with an OH group. That is going to be our ethanol, like we saw earlier. This is the carbon that is attached to the OH group. It is attached to 1 other carbon. This would then be a primary alcohol in this particular case. Coming down here, we have 1, 2, 3, 4, 5 carbons. So that's going to be pentanol. Given our OH group, the smaller number would be numbering this way, and that means that is going to be 2-pentanol. And again, looking at our group that is attached there, that is going to be 2-methyl 2-pentanol. In terms of classification, our carbon here is directly attached to 1, 2, and 3 carbons. This is a tertiary alcohol in this particular case. And this is essentially a ring structure. It is essentially the square. The square basically has 4 carbons attached to it. 4 carbons is based off of butane. It's a ring structure, so that is cyclobutane. It is a ring structure with an OH group, and it becomes cyclobutane. butanol in this particular case. And kind of like the other one there, that is our carbon that's attached to our OH group, attached to one and two other carbons, giving us a secondary alcohol in this particular case. Any questions on any of those reactions there, or those naming? Okay. So that's a little bit of review, some stuff we talked about in discussion last week or so. Let's also talk about some reactions that alcohols undergo. So we saw with alkenes that we can make an alcohol. So a reminder that if we have an alkene, which is our double bond, and we add water to it, we are essentially going to, I'll go over here, make an alcohol. So we could go from an alkene to an alcohol. So when we do a dehydration, we're essentially going to lose that water, and basically we're going to go backwards. So this is basically the backwards reaction. We're going to start at an alcohol, we're going to lose the water, and we're going to end up with our double bonded alkene. So it's kind of the reverse reaction. So how do we lose the water? This sulfuric acid here is just, again, a catalyst. Sometimes they may even write H plus on top to indicate that it's an acid catalyst helping out in this reaction. But just like the alcohol goes on, so if you remember, the alcohol goes on with a OH group on one carbon and a hydrogen on the other. When you lose the water, you lose an H on one carbon and an OH on the other carbon, and then you make a double bond between those two carbons. So in this reaction, again, nothing else changes other than hydrogen off of one, OH off of the other, and between the two carbons where you remove those things, you basically just lay in there a double bond and you're all good in that particular case. So let's take a look at some of these here. Oops. So here again, in this particular case, we're going to lose an H and an OH. And again, they're on different carbons. And where we lose that H and OH is where we make the double bond. Everything else is exactly the same. So that is exactly the same. This part of it is exactly the same. The only difference is right there. We're going to basically make a double bond. Same thing here. If we take it off a ring type structure, we're going to take the H off of here, OH off of here. Again, technically speaking, two different carbons, and that is where we should make our double bond. Again, nothing weird happens here. It doesn't open up or anything like that, but we make that double bond right where we took that H and OH off, basically to make water in that particular case. So for example here, if it doesn't make a difference, so what I mean by that is, again, if it doesn't make a difference, there's really no options in terms of what you take off. So for example, here on the top one, there's the OH group, and then we need to go to the carbon next to it to take an H off. And there's really no other option but that. But if you did have perhaps an option, so let's just say we had something like this. See if I could do this correctly here. I'll do this, and we'll do something like this. So let's say we had this guy and we want to do a dehydration of it. And again, really the sulfuric acid not going to do anything other than, again, act as really a catalyst to do that. Now, what I mean by this is we're definitely going to remove the OH. But then we have some options. We can perhaps remove the H over here, or we can remove the H that's over here. And depending on sort of which one you remove, will give you two different products. So I'm going to call this number one, and we'll call this guy number two. So let's say that I removed hydrogen number one. And what that would mean is I would end up with something that looks like this. Again, nothing's going to change other than I'm going to take that hydrogen off of there. I'm also going to take the OH off of this guy, and we would come across here and everything else would pretty much remain the same. Now, because I took the H off of the guy on the left and the OH off of the guy there in the middle, that is where I need to put my double bond to make sure everything's correct. So I need to lay up my double bond right about there. Now, my other option would be if I took off, say, hydrogen number 2, and we'll draw that guy down here. If I took off hydrogen number 2, again, everything will remain exactly the same, except I'm obviously going to take off my OH group here. And I'm going to take off that hydrogen number 2 here and keep everything else pretty much the same. And that would mean is because I took off the hydrogen between these two guys, that's where I should put my double bond over here. And as you can see, it gives us two different products. And this happens sometimes, just like if you remember when we put the HOH on or HCl on, we give the H to the one that started with the most hydrogens. And that's where we essentially will put our H on to the one with the most when we put on. So when we take it off and there is an option, we technically take it off from the one that has the least number of hydrogens. So we actually would take it off of this guy here. And this would give us our major product. So it's sort of opposite the way it comes on when there's an option. This would technically give us our major product. This would be our minor product. For our purposes, probably if you drew either one, you'll be okay. But technically speaking, probably this would be the major one that would happen. Again, when we put on the H, it goes to the one with the most. When we need to remove the H in a dehydration reaction, it goes to the one with the least. So sort of the opposite way that we put it on. Any questions on that? So dehydration reaction, pretty simple. You take an OH off of a carbon, and a carbon next to it, you take an H off of it, that gives you your water, and then you basically lay up a double bond between those two carbons. Absolutely everything else remains exactly the same. And again, that's a really important theme when you're drawing these reactions. Nothing really changes except for one specific part of the molecule when you're doing that. So we talked about some oxidation reactions here. And again, the oxidation reactions of alcohol, mainly what we're looking at here is the loss of H2. So we're going to remove two H's, and the H's that gets removed when you go through an oxidation reaction, which is what this symbol represents, oxidation reaction, is we always take the H from the oxygen, and again, the H from the carbon that's attached to the oxygen, and that's going to give us our H2. And that is exactly where we then would put our double bond on the other side between those two things. So in an oxidation reaction, two hydrogens come off, one from the oxygen, one from the carbon attached to the oxygen, and then you double bond it right between those two, the carbon and the oxygen. Absolutely everything else stays exactly the same. Here's some oxidation, again, by replacing some carbon-hydrogen bonds with oxygen-containing bonds. And as we go kind of this way here, we added some oxygen. We then remove some hydrogen, which is an oxidation definition, added some oxygen, and added even more oxygen sort of over here. Actually lost some hydrogen. So again, that gaining of oxygen, that losing of H2 is a classic sort of oxidation reaction that we see a lot in organic chemistry when we look at it. Now, depending on the type of alcohol you're dealing with, depends on pretty much what you will make. So let's talk about, again, what happens with our primary alcohol. So again, here in our primary alcohol, we're going to remove the H from the OH, H from the carbon. That will give us our H2. And with those two guys gone, we're going to put a double bond between the carbon and the oxygen. And that will make an aldehyde, is what this guy is. And again, that has the functional group that looks like this: carbon oxygen double bond with the hydrogen. And again, our primary alcohol, when you oxidize it, makes an aldehyde. By the way, if you do the reverse reaction and you add H2 to it, that is a reduction reaction. And you can take an aldehyde back to a primary alcohol by doing the opposite reaction. We will see this when we talk about aldehydes and some carboxylic acids later. But if you continue down this path and you put this aldehyde through an oxidation, we actually will insert some oxygen here, which is a definition of oxidation. And we get this type of guy here, which is known as a carboxylic acid, which is another organic compound that has a functional group of, I'll just draw it up here, carbon, oxygen, OH. So that is the functional group of a carboxylic acid. So the first step is, if you oxidize a primary alcohol, you will get a aldehyde. If you oxidize it one more time, you will get to a carboxylic acid, which we'll also see a little bit later on in another chapter as well. Now, if you have a secondary alcohol, and again, this is a secondary alcohol, same deal. We're going to take the H off of the O, H off of the carbon that's attached to the O. That gives us our H2. And then right here between our carbon and oxygen, that is where we're going to put our double bond. Again, absolutely everything else is the same. Nothing else changes other than that. And when you do this reaction here, this is a secondary alcohol. This goes to what is known as a ketone. And that is a carbon, 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 3 carbons in a row with an oxygen double bond in the middle. And if we oxidize our secondary, we do get that ketone. And by the way, if we go opposite there and you add H2 to it, that's the reduction reaction, and you will go backwards to an alcohol. So oxidation gets us to a ketone. If you want to go back, throw the H2 back on. H2 comes back on just like this. It very much breaks that double bond, H to one, H to the other, and it goes backwards. And we'll see that a little bit later on in this chapter as well. Now, when we get to a tertiary alcohol, we are going to remove that H from the O, but we cannot do the oxidation reaction because there is no second H. So we are missing that second hydrogen that's needed for this oxidation to occur. And when we try to oxidize a tertiary alcohol, we will not get any type of product. Any questions on that there? So let's take a look at a couple of, try a couple here just to make sure. Where can I probably throw it there? That'll work. So why don't you draw the product of each of these reactions just to make sure. Let me see here. Let's try this one here. Let's do this one here. And let's do this one here. All right, so take a couple minutes there and see what you come up with. Draw the products of each of those reactions and see what you come up with. Okay, so let's take a look. So here, again, sometimes it might be easier just to draw everything out so you can kind of see all the bonds. So if we kind of draw this guy out, kind of looks like this. By the way, this is a primary alcohol. So if you know it's a primary alcohol, you know that it actually should end up as a aldehyde. And that basically means we're going to take our H off of the oxygen, and we're going to take an H off of our carbon that's next to it, that's attached to the oxygen. Everything else is going to be exactly the same. So I'm going to draw it exactly the same. And we'll look something like this. And we will get our H2 that comes off. And then remember what happens now between the carbon and the oxygen, we get a double bond. And again, this is an aldehyde on its side. And so we get our aldehyde that is over here. Any questions on that particular one there? Coming over here to this alcohol, again, this is our carbon that is attached to the OH group. It is 1, 2, and 3 carbons attached. That is a tertiary alcohol. And from your knowledge, you should know that you will get no reaction in this case. Again, you will get no reaction because you do have the hydrogen there, but you are missing that second hydrogen there. So no second hydrogen. So it will not go through an oxidation reaction in this particular case. That leaves us our last one there. And if we identify the type of alcohol here, again, that's what we got on the bottom there. So that is our carbon attached to 1 and 2 other carbons. That is a secondary alcohol. So it will go through oxidation. And actually, I'll just borrow down here is the picture. We're going to lose the hydrogen here. And there is a hydrogen attached to that carbon. We will lose the hydrogen here. So those 2 hydrogens will come off to make our H2. Everything else will be the same, which means around we go in a square. And our carbon oxygen now becomes double bonded. And again, here we get a ketone. And that happens to be what is known as cyclobutanone because it's a ketone. Any questions on those reactions there of alcohols going through oxidation reactions? Okay. All right, then let's talk about another group of organic molecules, and those guys are what are known as ethers. And those guys are here somewhere. There we go. So ethers have pretty much the functional group of it's a carbon attached to an oxygen attached to a carbon. So that's sort of the functional group here of an ether. It is similar to water. It has basically 4 electron pairs and 2 bonds. So it does have that bent or V-shaped at 109.5 in terms of its geometry. There's many different ways that we name, or a couple different ways we name ethers, but for our class, we'll go with the common way of naming it, and it's fairly simple. You pretty much go to the oxygen, and you look at the group to the right, and you look at the group to the left, and if they happen to be 2 different groups, you name them in alphabetical order and just put ether at the end. In this case, they happen to be the same group, which is methyl, so we just call it dimethyl ether. So that's the way that we will name ethers here. The IUPAC way of naming is a little bit more different. This guy would be something known as methoxymethane. Methoxy because this is a methyl group with, you put oxy at the end of it, and the longest carbon chain is a methane. And that's how you would come to that IUPAC way of naming. So for us, we won't go that way. We're just going to go kind of the common way of naming, again, to the right, to the left of the oxygen, and put those groups in alphabetical order with ether at the end. So here's an example. Again, we go to the oxygen, To the right, we have an ethyl group. To the left, we have a methyl group, alphabetical ethyl, methyl, ether. Again, if you were going to go more IUPAC way of naming, this would be something like methoxyethane. It would be the name of this guy. Coming this way, we have two ethyl groups, one on each side of the oxygen. And again, we have diethyl ether. It would be the way that you would want to name it. So we'll go with that for ethers, the sort of the common way of naming it. And that's what you need to make sure you know how to do that. Now, in terms of ethers, they do not contain a hydrogen on that oxygen. So it cannot hydrogen bond. But it is a polar molecule. So the oxygen is more negative, really, in that sort of sense. This side is more positive coming this way. And it is able to do some dipole-dipole sort of interaction, but it cannot hydrogen bond. So if you remember in terms of the strength, we have our hydrogen bond as sort of our strongest, our dipole-dipole as our next, and then lastly, our weakest is our dispersion forces. So here, these ethers are going to probably be using sort of dipole-dipole interaction. So in terms of something like boiling point, we would expect to find the ethers having a lower boiling point than alcohols. Again, alcohols having the higher boiling point because it has that ability to hydrogen bond. Alkanes would have the weakest. And then we would have our alkanes, we would have our ethers, and then we would have our alcohols, again, in terms of higher boiling and melting points because of that. Any questions on that? Now, just because it does not necessarily have a hydrogen and it cannot hydrogen bond with itself, it can actually still able to participate with hydrogen bonding with some other type of compound like water, for example. So even though, like I said, it really can't hydrogen bond with itself. And when we talk about highest boiling points, lowest boiling points, we're really talking about sort of the intermolecular forces between themselves, basically, like butane and butane is going to use dispersion forces. Ethyl methyl ether will use dipole-dipole with itself, and 1-propanol will use hydrogen bonding with itself, and that creates those higher boiling points and melting points that we see. But because ethers have that oxygen and they are polar, they actually can hydrogen bond with, not themselves, but they can hydrogen bond with water through that oxygen and the hydrogen in water. Hydrogen and water being more positive, oxygen and the ether being more negative. We have that opposites attract, a bond between a hydrogen and an oxygen, which is hydrogen bonding. So about 5 carbons or less, we do have ethers that are fairly soluble in water. They're also obviously soluble in organic solvents, especially if you get over 5 carbons, they will be soluble in there as well. So 2 things here: ethers cannot hydrogen bond with itself because it does not have a hydrogen, and that's why it has a lower boiling point than an alcohol that could hydrogen bond with itself. But it can participate in hydrogen bonding with something like water because the water is supplying the hydrogen that's positive, going to be attracted to the more negative oxygen in the ether, and that's going to create a hydrogen bond, again, not with itself, but with other molecules like water. Again, though, much like anything else, if we get a lot more carbons involved, the molecule itself gets larger, there's a lot more carbons in the way, and it makes it really hard for it to interact with something like water. So we see a very big drop in the solubility as you go above kind of 6 carbons in terms of ethers. Any questions on that there? So ethers are used as sort of general anesthetics. Diethyl ether was the first one. Now they've sort of popped off a lot of the hydrogens and replaced them with sort of fluorines. And again, it has some better sort of effects than a straight old ether and stuff like that has all those hydrogens. Not such a bad after effect, I suppose, in terms of that. Any questions on ethers? So ethers, you need to be able to identify an ether by its functional group. You need to be able to name simple ethers using the common method, alphabetical groups on each side with ether at the end. And you need to know, again, where ethers fall in terms of sort of boiling points and stuff like that. Any questions on that there? Okay. So alkyl halides, we sort of talked about really when we talked about alkanes, when we put a halogen on, basically an alkane, we do get an alkyl halide. Alkyl just means carbon, halide means a halogen's involved, and it basically happens with those kind of substitution reactions that we talked about with alkanes, where a hydrogen comes off, a halogen comes in and attaches in there. And you can name it kind of very much like you can name carbons or classify it. This is a primary, secondary, tertiary. Again, the carbon that has the halogen attached to one carbon, primary. Carbon attached to the halogen attached to two carbons, secondary. Carbon attached to the halogen attached to three carbons, a tertiary alkyl halide. Now, alkyl halides, they typically have boiling points and melting points. It does increase with size. Boiling points and melting points increase with the halogen that's involved. And that's because usually this bond here is a polar bond. Again, if you remember in terms of electronegativity, highest electronegativity right here at fluorine, up and to the right. So that is sort of where we find all of our halogens, basically, our fluorine or chlorine or bromine or iodine going that way on the periodic table. So in terms of boiling points, we do see it does increase with increasing size. And again, as you can see here, higher boiling point, bigger molecule. Going to be helped out with more electrons and all that kind of stuff. So to name these, we're not going to really go over this because we kind of did already in like the first chapter. Again, we would put it in there: chloral for chlorine, fluoro for fluorine, bromo for bromine. So we sort of covered, kind of how to name these guys here. All right. Any questions on alkyl halides? That brings us to another organic group, and really for alkyl halides, they sort of really do fall in that sort of alkane conversation that we had in that earlier chapter. The next one is a thiol, and the functional group of a thiol is actually a sulfur-containing group, so an SH group. So the functional group of a thiol is this guy. It is very similar to an alcohol, except that it obviously has a sulfur involved. So instead of an alcohol, we have a sulfur. And if you look on the periodic table, here's oxygen, here's sulfur. They're in the same group, so they have very similar sort of properties, and so does thiol. So they do behave very similar to our alcohols here, except obviously an alcohol has that OH group, while the thiol here has that SH group that's attached. But very similar in terms of geometry as well. It has 4 electron pairs and 2 bonds, which would be our bent or V-shaped. But thiols do not contain an OH group, so they cannot hydrogen bond. So remember, in order for something to hydrogen bond, you do need a bond between hydrogen and either nitrogen, oxygen, or fluorine. So you kind of need those guys involved there to allow something to hydrogen bond. And as you can see here, we see a much lower boiling point for a thiol than an alcohol. Again, our alcohol here does have the ability to hydrogen bond, does not have the ability. And we do see that difference there in terms of our boiling points. You're not going to have to worry about actually naming thiols, even though just to kind of give you a hint as to how you would name it, that is 2 carbons. So that is ethane, and then you put thiol at the end. So basically 2 carbons, ethane, and the SH group is a thiol. So it's basically known as ethane thiol. And I think we will probably stop there, I think, for today. Any questions up to that point? And we'll talk more about, we'll finish this little bit about thiols next time and continue on with the rest of this chapter. Any questions on anything? Okay, if you have lab, have a good lab, have a nice weekend. If you have discussion, also have all those things, but I'll see you in discussion in about 5 or so minutes. Other than that, if you're out for the weekend, have a nice one. And